Hi, I'm going to talk a little bit about the Fibonacci sequence. I'm going to start off by drawing a sequence of rectangles that I'm going to grow from the upper left-hand side of the screen down to lower right, and at each step I'm going to add a new square, and I'm going to put the new square adjacent to the last two squares that I drew. So here's the next rectangle. Here's the next rectangle. What's going to happen is we'll see a pattern emerging in the sizes of each of these squares. I'll draw one more square. This is going to be the last one I can fit on the screen. Okay, now let's take a quick look at the size of each square. These two squares have size 1. This square is size 2 because each side has length 2. The sides here have length 3. The sides of this square have length 5. The sides here are going to be 8. And then finally for this big square, 13. Let's take a look at what the sequence looks like when I write down the numbers. The first two squares we had here had sizes 1, 1, and the next square had size 2, then 3, 5, 8, and 13. And you might be able to figure out what the next square would have looked like. It would have had a side whose length was 8 plus 13, so that's going to be 21. And the next guy after that would have size 34, and then 55. And the sequence keeps going forever. So this sequence is called Fibonacci sequence. And if you're like me, you're probably a little bit curious about where that name comes from. So it turns out that a long time ago, many hundreds of years ago, there was a guy named Boccaccio. And he was an Italian guy. He lived in this city called Pisa, Italy. And you might think, well, Boccaccio sounds like Fibonacci. Maybe he invented the sequence. But you'd be wrong. It's actually his son, whose name is Leonardo, so they would call him Leonardo of Pisa, who is credited as having invented the sequence. Actually, Indian mathematicians knew about the sequence a long time before Leonardo did, but because the Western world didn't really know about that, like Western Europe, they give credit to this guy. And so the name Fibonacci comes from the son of Boccaccio. Like in Italian, you might say Filius Boccaccio. You might abbreviate that as Fibonacci. So that's where the name comes from. That was around 1202 is when he published the book. Okay, so I'm going to draw a table of values for the Fibonacci sequence. And I'll draw two columns. On the left, we'll have n. And I can just count up 1, 2, 3, 4. And on the right-hand side, I'll write capital F sub n, and what this denotes is what I'm going to call the nth Fibonacci number. So this is the first one, the second one, the third one. So F sub 1 is just 1. F sub 2 is also 1. Then 2, and then 3. I'm just rewriting the sequence. And now we might get down to a certain step. We say, okay, well, what's the 10th Fibonacci number? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, that's 55. And what if someone asks you, if I plug in n equals 100, what's f sub n? So you might think to yourself, okay, well, if I knew the last two numbers, there's a way I could figure this out. Mathematically, what we want is a way that we can write down a formula for the nth Fibonacci number. So far what I've done is I've just given you a drawing with rectangles and written down the first part of the sequence. I haven't given you a rule yet that lets you figure out what the nth number is. And that's important in math, is to know how to figure out any number in an entire sequence. So right now I'm going to give you a rule that will help you figure that out. We'll say the first number has to be 1 and the second number has to be 1. So that's not really helpful. That only gives us 2 of the numbers. But in general, we could say that the nth number has to be equal to the one before it, f sub n minus 1, plus f sub n minus 2. So these 3 equations together will let us figure out any of the Fibonacci numbers at all. And to let you know what this last equation is called, it's a special type of equation called a recurrence relation. The reason it's called a recurrence relation is that it tells you the next value of a sequence using the previous values in the same sequence. Now what I've done is I've just drawn out the Fibonacci sequence here with a few more terms on the end, and I'm going to show you a few patterns. I'm not going to prove these patterns to you, we're just going to notice that they work for the beginning of the sequence, and it might be interesting for you to think about whether or not these patterns really exist for the entire sequence or if they just happen to be a coincidence for the beginning. Okay, so first let's look at the even Fibonacci numbers. 2 is the first even one, then 8 is the next even one, 34 is even, these guys are odd, 144 is the next even one, and you might already see a pattern here. This is the third Fibonacci number, this is 6, 9, 12. It looks like every third Fibonacci number is even. Is that pattern a general pattern, or is it just existing for the first few Fibonacci numbers here? Okay, here's another pattern that I can notice in the numbers. Let's say that I add up the beginning part of the sequence. So the first one is just 1. Then I'm going to add up the first 2 Fibonacci numbers. I'll get 2. If I add up the first 3 Fibonacci numbers, I get 4. Then if I add up the first 4, I'll have 7. The first 5 give me 12. The first 6 give me 20, 33, 54, etc. If you look at this sequence here, it actually looks pretty similar to this part of the sequence here, -1 for each of the terms. So the question is the sum of the beginning part of the Fibonacci sequence plus 1 always going to be another Fibonacci number? Okay, the last pattern I want to look at is a little more complicated. What I'm going to do is I'm going to take 3 numbers in a row from the Fibonacci sequence, and I'm going to look at the outside numbers multiplied together. That's 2 times 5 gives me 10, and then I'm going to look at the square of the middle term. 3 squared is equal to 9. Okay, these guys are pretty close. They're 1 off. Let's try a different pair. Let's try 5, 8, and 13. 5 times 13, well, it's going to be 50 plus 15, that's 65. And then the middle guy is 8. 8 squared is 64. Again, they're pretty close. Only 1 off. Okay, let's try one more example just to see if that pattern seems to be continuing. Let's try 13 times 34, 442, and then the middle number is 21. When I square that, I'm going to get 441. Again, these two numbers are pretty close, off by 1. I can summarize that last idea with this equation, which is basically saying if I have 2 Fibonacci numbers that are around a middle one, f sub n, then if I multiply the outside ones, that's the n minus 1 and the n plus 1 in the subscripts, I'll get the square, maybe plus or minus 1. Okay, one last pattern. Now this pattern is pretty interesting because unlike the other ones that mathematicians have already figured out, this one is still kind of unsolved. It's an open problem in math. 2 and 3 are prime numbers. Let's see, 5 is a prime number. 13 is prime. 89 is a prime number. And 233 is a prime number. But mathematicians still don't know if there are infinitely many prime numbers in the Fibonacci sequence. I'll leave you with the question, how many prime numbers are in the Fibonacci sequence? I have to warn you, this is probably a pretty hard problem because no one's solved it yet, but if you do happen to figure it out, you'll probably be kind of famous. Good luck.